Hi, Java students. I am going to talk to you today about recursion. This is my recursion lesson to introduce it. I know you already had an introduction by watching another video and trying some things yourself, maybe on CodeHS or maybe with Mrs. Westerland on the AP YouTube channel. But I had some notes put together, so I thought I would go through them just to finally, this is probably the last actual topic that I will teach you for the year. We're just going to practice it a little more, and then maybe we'll do something fun for the rest of the year together. Maybe we'll do graphics. That would be fun. I hope we can do that. So anyway, recursion is, to understand recursion, you must first understand recursion. Let's have a little fun with a recursive cartoon. I got this from XKCD. It's kind of a cool website. You should check it out sometime. There's a link here. Very intelligent humor. But okay, so if you look in this picture, you can actually see the cartoon in the picture, and then inside that cartoon's picture, you can see the cartoon again. And I don't know how small they ended up going, but it's basically the cartoon inside of itself, infinitely, in theory. And that's recursion. But we don't want it to be infinite in programming. In programming, a recursive call is a method that calls itself. Here's another illustration. Imagine you find a locked suitcase in your grandmother's attic. She says the key is somewhere in the nearby box. When you open the box, you find it is full of other boxes. You could solve this problem in two different ways. An iterative approach would be to make a pile of boxes to look through. And as long as the pile isn't empty, you grab a box. If you found the key inside that box, you are done. If you find a box, then you add it to the pile of boxes, go back to the pile, and while the pile is still not empty, grab another box. If you find a key inside there, you're done. If not, if it's just a box, go back to the pile and get another box, okay? Or if there's a box inside that box, you would still have to keep going and find a key. A recursive approach would be to go through every item in the box. If you find a key, you're done. If you find a box, you go through every item in that box. If you find a key, you're done. If not, you go through every item in that box. So it's just kind of like one inside the other nested type concept. So why recursion? Does recursion usually make code faster? No. Does it usually require less memory? And the answer is no. Then why use recursion? Sometimes it makes your code simpler. Somehow, let's see. So here is a first example that's actually not a good example. Okay, you can write something you think is recursive because it calls itself. That's the main definition of a method that's recursive, is it makes a call to itself. But some methods that call themselves are not good examples of recursion because they don't work. Okay. For example, this print method. If you send it a number, it will print out that number and then it will call itself with the next bigger number. Okay. What's the problem here? If you put in a 1, it will print out a 1 and it will call itself with the number 2. Then that will print out the number 2 and call itself with the number 3. Then print number 3, call itself with the number 4, etc. There's no way for this to end. This ends up being called infinite recursion. You will get a stack overflow error. You heard that before. So the first rule of recursion is that you must have a base case, a condition under which there is no recursive call, no call to the function itself again, so that we prevent infinite recursion. Here's a second version of the print method. It now has a base case. This right here, if k is less than 0, return. Okay, so now if we send it something less than 0, we know it will return and not call itself. So if we send it a 1, Is there a chance that it could possibly not infinitely recurse and overflow the stack? Let's see. Let's trace it out. If we send print 1, k becomes 1. 1 less than 0 is false, so it skips over this return. It prints out the value of k as 1, and then it calls itself with 2. So now on that call, k is 2. 2 is not less than 0, so it won't return. It will print 2 and then call itself with 3. This is no better than the one before. Even though we provided a base case, we're not getting any closer to returning back and ending the infinite recursion because our numbers keep getting bigger and it's only checking for something less than 0. So the second rule of recursion is that every recursive method must make progress towards the base case to prevent infinite recursion. So here's a version that will not cause an error. It will not overflow the stack. It will not infinitely recurse. It will actually return eventually and stop recursing. Still making a call print 1, but this time we are going to check if k is greater than 5. In that case, then return without doing a call to print line, because you know that the return statement is kind of a final statement in a method. Nothing after a return statement gets executed, right? So that's why this works. Because on the first call, 1, it will skip over that base case because it's not true. And it will print a 1 and then call k plus 1, print 2. On that run, it will also skip the base case because it's not true, print out a 2, call print 3. On that run of the method, it will skip the base case, print out a 3, etc. When we finally get to calling print 6, then it will come in here and see that 6 is greater than 5, and it will not print 6 or call print 7. It will just return back. So what will have happened by that point is we would have printed out the numbers 1, 2, 3, 4, and 5, and that's it. Then it ends the recursion. I want to move on. Okay. We need to understand what's really happening behind the scenes when we make a recursive call. What actually happens is that the method clones itself. So in the computer's memory, it's like making a new copy of the code, any local variables that are in that method in their initial states, and the value parameters, basically any parameters that are not passed by reference. So if it's something that would be making a copy like one of the primitives, then it will make a copy of that parameter and have the value that comes in as the argument. When the method returns back, that whole clone goes away, but the previous ones are still there. So there's kind of like this stack of method calls and everything related to them saved in memory. Okay. All right, so let's examine some examples. This one is called mystery. We don't really know what the point of it is, but it is recursive because it calls itself. Take a look at this code and determine, do you think there are any values of k for which this is dangerous, like it would have infinite recursion? Do you see that? If the base case is just checking whether k equals 0 to return, and it's always subtracting 1 from k to make the next call, then which values of k would it never return for? Basically, if k started out being less than 0, because it would keep going further negative numbers and you would never get k equals 0. If a precondition was that k had to start out, like you had to make the parameter have a positive value greater than 0, then you'd be safe. But one way to improve this and avoid that problem altogether would be to change the equal 0 to perhaps less than or equal to 0, because you know that from the recursive call being k minus 1, the numbers that it calls the next, that it makes the next call with are always going to be smaller and smaller and smaller. So they're going to keep getting smaller. So therefore, you want your base case to check something that it can't go past. And even if it starts in a certain spot, it will return. So we want to make this if k is less than or equal to 0, then return. Here's example 2. What would happen when we call this version of mystery? Okay, let's just read the method. It's a void method. It has no parameter. It creates a local variable called k, that's an integer, with a set value of 3. If k equals 0, it will return. Otherwise, it will print out k plus a space, it will decrement k by 1, and then it will call itself. So on the first call to mystery, the local variable k starts off 3. Is that going to be ever equal 0? No. That return is not going to happen if k is a local variable set inside the method and initialized with a value of 3. K will never equal 0 because you're not sending it in as a parameter from a previous call and modifying it that way. Even though in this else statement, it modifies the value of k before calling mystery, remember that on a previous slide, we mentioned that when you make a call to a recursive function, a whole new copy of that method is created, and its local variables have a whole new copy starting fresh with the value of 3. This value of k, when you call this second call to mystery, is going to once again be recreated at an initial value of 3 and then checked against 0 and still not have reached the base case. And it never will, even if there's this else clause that decrements k. On that next call, k is going to be set back to 3 again because it's a local variable k, not a parameter. Okay, so that's something to watch out for. Local variables, whole new copy is made for each method call. All right, this says trace and predict the output. I'm going to give you a minute to look at it. Okay, I got myself set up and ready to trace this out with you. Take that minute to look at it while I go let the dog in, and I'll be right back. Okay. Rocky, you want to be in the video? Come here. Come here. Here's Rocky. He just came in from outside. Did you catch any squirrels out there, Rocky? I didn't think so. Okay. All right, so let's trace through this together. On the first call to mystery, let's say that we call mystery 4, okay? It says if j equal, int k is created, okay? But 4 is actually the value of j. 4 is the parameter. So if j is equal to 0, we return. We won't. Otherwise, k gets j. So k is going to get the value 4. And then it's going to call mystery of j minus 1. J is 4. So it's going to call 3. Then when it returns from that call, it's going to print out the value of k plus a space. Okay, but now let's think about the call to mystery 3. In that case, k is going to take on the value of j, which is 3, and then it's going to call mystery of 2, because j minus 1. Okay, then it won't actually print anything out until later when it finishes the call to all the other methods. Mystery of 2 is going to start with j is not equal to 0 still, because j is 2. K is going to take on the value of j, and then it's going to call mystery of 2 minus 1, which is 1. And inside that call, still j is not equal to 0, so it's not going to return. It's going to go to the else part, and k is going to get the value of j, which is 1. And then it's going to make a call to mystery of j minus 1. 1 minus 1 is 0. And when it gets into that call, the mystery of 0, in this case, j does equal 0, so it will return without doing anything. Okay, so this does not output anything. There's nothing output from the call to mystery 0 because it never gets to that else part. Okay, it just returns back. When we get back to this call, now it's going to print out the value of k and a space. What's the value of k? 1. So there's going to be 1 and a space. I'm just going to put all the output here. So it's going to print 1 and then a space. Okay, that concludes this call. Now it's going to kick back to the previous call and conclude that call by printing out the value of k plus a space. Okay, then that one is done. So it's pretty much going to toss that off the stack, kind of gone. Kick it back to this call where k was 3, printed out with a space, and then kick it back to this call, print out the value of k, 4 and a space. So the final output from this would be 1, 2, 3, 4. Okay. You could always try to take any of these methods and put them into an editor and make a little main method and call them just to kind of play around and see how they work. So I was alluding to the fact that at runtime, a stack of activation records is maintained by your compiling environment. Okay, BlueJ, Replit, there's many others, places where they know how to translate Java into executable code. Behind the scenes, there is a stack of activation records for each active function. So each activation record includes a copy of the method's value parameters, the method's local variables, if any, and the return address of where to go back to finish that method call wherever it was left off. So when a method is called, its activation record is pushed onto a stack of activation records. When the method returns, its activation record is popped off the stack, and then the return address is used to determine what to execute next. All right, so let's consider these two versions of this method called read and print. Okay, version 1, if it were just called read and print, there was a call made to this function. First thing that would happen is there'd be a variable called C that could store something of char type. That's a single character that would be created. And C would get the next thing from the reader. That would be, input from the input stream. So the reader would send a V that would be contained in C. And then system.out.println C, so the output would start off by printing out, it says just print out C. So the first thing that would be printed out is a V. And then if C is not equal to a period, I almost forgot to put a period at the end. If C is not equal to a period, then it will call read and print again. So on that second call, it's going to recreate a new copy of this C value. So I'm going to put a new copy of C up here. And what's going to go into it is the next thing off of the reader. So this would have been pulled off the reader. It's no longer there. The next thing up is an O. So that's going to go into the char C. And then it's going to print out the value of C. So that would be here. The value of C is O. And then if C is not equal to a period, it will just call read and print again. So the next time it calls read and print, we would end up having another copy of C created. Okay, I'm going to stick that on top of there. And what goes into it is, that was removed from the reader. The next thing coming from the stream would be an L, so that goes into C. And then it will print out whatever's the contents of C to the stream, to the output. And that would be VOL, etc. It's going to go one more time, actually two more times. The next time, it's going to create another copy of C. The next thing up is a Z. That's going in there. It's also going to be printed out. Then another copy of the function is going to happen. Okay, this time the value of C will be a dot. Okay, whoops. And that, now on this particular call, when it gets a dot from the reader, it's going to print that out. And then it's going to evaluate if C is not equal to a dot. Oh, it is equal to a dot. So it's not going to call any more read and prints. Okay. So after that, it would kind of clean up and be like, okay, I'm done with all of these. I can go back and kind of finalize each of the methods and they all go away. Okay, that would be the run for version 1. All right, so now let's take a look at version 2. In this version, still same read and print, still creates a local variable C for a character. It still takes something off of the input stream buffer, but this time it compares it. If the value is not equal to a period, then it will read and print. Otherwise, it will print out the value of C. Okay, so let's go through this one step at a time. On the first call to read and print, the first character to come off the reader is V. That's now the value of C. And then if C is not equal to a dot, all right, it's not equal to a dot. So it will call read and print. But it didn't print out the value of C yet. Okay, so then on the next copy of the method, it's just going to go and start a whole new char C. Okay, like a new copy. It's going to take the next thing off. It's going to put it into a new copy of C. And it's going to evaluate, is that equal to a dot? No. So the condition is true, and it will call read and print right away, but it hasn't printed out C yet. It's going to wait till later when this call gets back to print out C. So calling the next read and print, it's going to now, in that third one, take the value of L off the stream, put it on into a local variable called C, evaluate. If it's not equal to a dot, which it's not, it will call read and print again, but did not print out anything yet. So it's going to do this for Z, and then on that one, finally we get to this character that is a dot, and it will fail the if test if C is not equal to a dot. This time it is equal to a dot, so it will not call read and print. It will skip to the finally get to the last line and print out the value of C. So version 2 output is starting with a dot. Then it's done with that call. So it kicks back to the previous call, which now has to complete itself by printing out the value of its copy of C. Its copy of C is the character Z, etc. They're going to keep on backing up. Now that one's done, so it can let the previous call complete its run, which means printing out the value of C, which is L, etc. You can see where this is going. It's going to reverse the characters that were in the buffer or the input stream when it goes to print them out, because it's waiting until after all the calls are finished in order to print out each character. So this brings us to recursion rule number 3. Sometimes a method has more to do following a recursive call. And whatever code is written after the recursive call gets executed only after the recursive call and any call it calls finish. Okay. Now, here's a few examples of recursive solutions to problems versus the iterative solution to the problem. There's the consecutive integer sum problem. If you wanted to take for a given number and sum up every number from 1 up to that number, that's called the consecutive integer sum. You can do this with a loop, iteratively, just repetitive, pretty traditional solution, starting with the sum being 0. Have the loop control variable k that starts with 1 and goes less than or equal to whatever value you're trying to compute the sum up to, max, and then just sum. Okay, that's a pretty simple algorithm, iteratively. You can also accomplish this with recursion. You can, if max is less than or equal to 0, return 0. Otherwise, return this function plus itself called with max minus 1. So where in this case, instead of adding from 1 up to the max, it's going to start with max and add the next lower value. And to that, add the next lower value. And to that, add the next lower value until you get to 0. And then once you finally are at 0, you would return 0, so that does not get added in. Okay, here's the factorial iterative version versus the recursive version. In the iterative version, you start with factorial equals 1. And if n is equal to 0, return 1. So if we're trying to find the factorial of 4, n would equal 4. Since n is not equal to 0, it's not going to return here. But if we did send in a value of 0, it would return 1. Okay. K is going to start with 4, the value given, and just go down by 1 integer until it reaches a 2. There's no really point in multiplying by 1 because it doesn't change anything. So they just have as long as k is greater than 1. And it's just going to take the variable fact that is containing the product and multiply itself by the value of k and return that value. That's the factorial in iterative version. The recursive version says as long as the input is 0, that's your base case, you would return 1. For all other cases, you're going to return that number times the factorial of the next lowest number. And so that's the recursive version. Okay. Any of these that you want to try in a browser computing environment, it might be interesting to just play around with it and get them to work. Then there's Fibonacci sequence. I think this was mentioned in the video you watched last time, possibly in the Code HS exercise as well. Take a look at, compare those two to each other and see how they both work. Okay. I'd like to just do one more example of tracing recursion with a method called PrintStars. Okay, take a look at the body of PrintStars. if you call the PrintStars function, sending it the number 4, like this call shows, then you're going to get a loop, a for loop, where j starts at 1 and j goes less than or equal to 4. So j will equal 1, 2, 3, and 4. It's going to do something 4 times at the very beginning of the call. I've kind of printed this out and marked it up a little bit. The pink stuff is what's going to actually be executed. So j will equal 1, then 2, then 3, then 4. And each time it will print out a star, just a star. So the output of that is going to be star, 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 star. Then it's going to print a backslash n, which is a new line character, to go to the next line. And then it's going to call itself again with k minus 1. So k minus 1 is like so. This time we are sending in a 3. So you could fill in the output for PrintStars 4 was 4 stars and then a new line character to take you to the next line. Then the next call is PrintStars 3. And since k will now equal 3, j is going to run from 1 to 2 to 3 and then stop. And each of those values of j, it's just going to do a printout of a star in a row. Then a new line character, and then call PrintStars of 2. PrintStars 2, the value of j is just going to range from 1 to 2, and each of those values of j is going to result in a printing out of a star. So there'll be 2 stars. And then when k equals 1 on the next call down the stack, j is going to just go be 1 and print out a 1. Okay. When we get to PrintStars 0, j is equal to 1 will not be true. I'm sorry, j gets 1. J is going to start at 1, but then 1 is less than or equal to 0 already, so it's not going to print anything. Okay, it'll just print another new line character and then call PrintStars again. I just noticed that this PrintStars example has no base case. It has no way of stopping the call to PrintStars for the next one. So it's going to go to -1 as k, and it's still not going to print anything as in terms of stars, but it will print a new line character. So this method is dangerous because it will just keep, basically, here's the output. If we call PrintStars 4, it's going to do 4 stars, then a new line character, 3 stars, then a new line character, 2 stars, then a new line character, 1 star, then a new line character, then a new line character, then a new line character. It's going to keep on printing out spaces that you can't even see. So that's really crazy because you'll think it's done, but it'll freeze your screen and it will overflow the stack, and then you'll have a problem. If it's not in a browser, it's in like a software on your, installed on your hard drive, you could crash the computer because of the infinite recursion. It will just keep on creating copies of itself, copies of that method, copies of the variables. It'll just keep using up space infinitely, and you won't potentially know what's wrong. So we would need to add a base case here in order for this to be doing what we kind of intended for it to do, which is to just print out, a little arrangement of stars. If this were a question on an exam, not that I'm giving you really any exams, but I might have you just do practice problems to submit, and it asked you what's going to be the output from this, basically this would be the output, okay? But if there was like a multiple choice option that said something about it causing an error, in this case, the way it's written, I would choose that because there's no base case for the recursion. Okay, there are a few more examples in your notes. There's factorial and mystery and Fibonacci that I would like you to just go through on your own and fill those things out. Write down each recursive call and what it returns, and then figure out what the final result would be. Okay, There's also an interesting example of how recursion could be used here to erase an object in a 2D array. If you think of a 2D array like what you see on the screen here, as just being a grid of either black and white, 1 or 0, then it could represent graphical objects, like in our picture lab, except they could even be colors. But anyway, very simple black and white objects here. This is a recursive solution that, depending on where it starts, it would just erase all black pixels, we could call them, or elements of the array that are around it, by using 4 calls to itself, going up, left, down, and right, using these different coordinates. Your row +1, same column. Row -1, same column. Same row, 1 column up, same row, 1 column, I should say right and left for columns, up and down for rows. So interesting. You may want to check that out in more when you have more time. Some other algorithms that are very classic examples of recursion would be the Towers of Hanoi solution. You may have heard of that in math class. 2 of the sorts that you'll hear from in the other videos that I send you, quick sort and merge sort, they are based on usually recursive solutions as well. So in summary, we would use recursion for clarity and elegance in our solutions, not really for speed or space savings. And you have to be really careful when using recursion. Every method must have a base case. Every recursive method must make progress towards that base case. Sometimes there's more to do following a recursive call, and then it kind of ends up reversing the order because it's going back through the stack in reverse order. Okay, so watch out for that if you're trying to trace recursion. And there is something called doubly recursive functions where they call themselves in more than one spot inside the body. In that case, you have to use a tree of calls. I'm going to save that for maybe another day, maybe not even this year, but you may see that again, and you would use a tree of calls. So this was my recursion lesson, and I hope you got something out of it so that you can try the practice problems next time. There won't be anything for me to check this time. I just wanted you to watch this lesson. Okay, and take notes, hopefully. Have a good night and enjoy Memorial Day weekend.